Welcome to the Explainer. Today we're going on a bit of a journey, an adventure really, through the world of numbers. We're going to see how every single type of number we use, from the ones you count on your fingers to some pretty abstract stuff, was actually invented to solve a very specific problem. So, let's just start with a really basic question. We all learn to count. 1, 2, 3. It's simple, right? So, why do we bother inventing all these other, more complicated kinds of numbers? Why not just stick with the basics? Well, the answer is that our whole system of numbers is kind of like a toolbox, one that's been built up over thousands of years. Every time mathematicians hit a wall, a problem they just couldn't solve with the tools they had, they didn't give up. They just invented a new tool. So let's open up this toolbox and take a look at the very first tool that ever went inside, the one that really got the ball rolling, the natural numbers. Right, these are the numbers we all know and love, the ones you use for counting things, for labeling stuff. And just so we're on the same page, for this explainer, we're going to include 0 in this set. It's something you see a lot in fields like set theory and computer science. Now, the natural numbers have this really cool property. You take any two of them, you add them together, you get another natural number. Same exact thing happens when you multiply them. Mathematicians have a word for this. They say this set is closed. And for a while, it probably seemed like, hey, this is perfect. This is all we'll ever need. But then we hit our first major snag, subtraction. I mean, sure, 5 minus 2 is 3, and 3 is a perfectly good natural number. But what happens when you flip it? What's 2 minus 5? All of a sudden, oops, our toolbox is broken. The answer we're looking for, it's just not in there. So to fix this, we needed a bigger toolbox. We needed an upgrade. And that brings us to our next brilliant invention, the integers. Integers, which get the letter Z from the German word for numbers, Zahlen, they solve our little subtraction problem beautifully. How? By basically creating a mirror image of all the counting numbers, the negatives. So here's the trade-off. What we gain is huge, the power to subtract anything from anything. Our number system gets way more powerful. But we do lose something a little subtle. Think about it. With the natural numbers, you can start at 0 or 1, and you know for sure that if you just keep counting up one by one, you'll eventually hit every single number in the set. That simple one-way street, it's gone now that you have to deal with negative infinity too. Okay, so our new integer toolbox is pretty great. We can add, subtract, multiply, no problem. But you guessed it, it wasn't long before humanity ran into the next wall. What happens when you try to divide one apple between two people? What's 1 divided by 2? Uh-oh, once again, the answer isn't in our set. And so, to solve this division problem, we had to go back to the workshop and invent yet another tool. And this one is called the rational numbers. The rationals, which get the letter Q for quotient, are pretty much what they sound like. They're all the fractions, all the quotients you can possibly make by dividing one integer by another. 1 divided by 2? Simple. It's the fraction 1/2. Problem solved. And with this tool, man, the power we gain is enormous. We now have a system where all 4 basic operations, add, subtract, multiply, divide, they all work pretty much perfectly. But as always, there's a trade-off. We've lost the idea of a next number. Think about it. With integers, the number after 5 is obviously 6. But what's the number right after 1/2? Is it 0.6? Nope, because 0.51 is closer. Okay, is it 0.501? You see the problem. The number line has become dense. Between any two fractions, you can always find another one, and another one, and another one. Now you might be thinking, okay, an infinite number of fractions. Surely we've filled up the entire number line now, right? It seems like it should be full. But, amazingly, it's not. It turns out there are still gaps, infinitely many of them in fact, and filling those gaps requires our next big idea, the real numbers. These gaps, it turns out, are filled by these mysterious numbers called irrationals. And their defining feature is that when you write them out as a decimal, they go on forever and ever, without ever repeating a pattern. The two most famous ones are probably pi and the square root of 2. Let's just take the square root of 2 for a second. This is a very real number. It's a length you can actually draw. It's just the diagonal of a perfect square with sides that are 1 unit long. But when you try to write it down as a decimal, it just keeps going and going and going, with no pattern in sight. You can never, ever write it down as a simple, clean fraction. And the way mathematicians prove this is it's beautiful.
It's a genius technique called proof by contradiction. They started by saying, okay, just for the sake of argument, let's pretend we can write the square root of 2 as a simple fraction. But when they followed that idea down the rabbit hole, they found it leads to a logical paradox, a contradiction that just can't be true. The only possible conclusion was that their initial assumption had to be wrong. It was impossible from the start.
So, okay, our number line is finally complete. We filled in all the gaps between the fractions. We're done, right? This has to be the end of the road. Well, not quite. There was one last, really stubborn problem that no number on the entire real number line could solve. And solving it led to the most powerful, and maybe the weirdest, tool in the entire box. Here's the problem. What is the square root of -1? I mean, think about it. A positive number times itself is positive, and a negative number times itself is also positive. So there is no real number out there that you can square to get a negative result. It seems impossible. And the solution that mathematicians came up with was just audacious. It was both incredibly simple and totally mind-bending. They basically just defined a solution into existence. They said, okay, we're creating a new number. We're going to call it I for the imaginary unit, and its one job, its whole purpose in life, is to be the number that when you square it, gives you -1. And once you do that, once you combine all the real numbers we already had with this brand new imaginary unit, you get the set of complex numbers. Every complex number has a real part, A, and an imaginary part, B. And the amazing thing is, with this final tool, it turns out you can find a solution to any polynomial equation you can dream up. The system is at last truly complete. And there you have it. That's how we built our entire universe of numbers. It's like a beautiful set of Russian nesting dolls, right? Each new number system fits perfectly inside the next, building on what came before to create something even more powerful. This chart really tells the whole story of our journey at a glance. You can see how we start with the naturals, where we can only really add and multiply. Then, boom, we get subtraction with the integers. Then we gain division with the rationals. And finally, with the complex numbers, we achieve this incredible property of being algebraically closed, which basically means every polynomial equation has an answer within the system. The only thing we had to give up right at the end was a simple way to order the numbers, but what we gained in return was just immense. So, we've seen this entire incredible structure was built piece by piece, not just for fun, but to solve real, concrete problems. And that leaves us with one last, really fascinating question to chew on. What's the next problem out there? What's the next great challenge that our current mathematical toolbox just can't handle? And what strange, new kind of number will we have to invent to solve it?